In the lecture 2, we discussed till this fundamental theorem of graph theory. So in the lecture 3 of advanced graph theory, I will continue with this theorem. So the statement is for any graph G which has n number of vertices and m number of edges, the sum of all degrees of vertices, is equal to 2 times sum of the number of edges, 2 times the number of edges. So we have to prove this. So to prove this theorem, let us consider. So since we have given it has n number of vertices, so let me call vertex set as vertex set, will say v1, v2 and vn. These are the vertex set, and edge set, I'm writing the proof of this theorem. Edge set is e1, e2 and em. There are m number of edges. So how to prove? So we have to prove that summation of degrees of each vi I from 1 to n, this is equal to 2 times number of edges. So I will there are different proofs in different books, so I will use the concept of incidence matrix. So if we write the incidence matrix corresponding to this graph, so incidence matrix, so let me denote it by m. Okay, so the row are the vertices like v1, v2 and so on up to vn, and columns are e1, e2 up to em. So what happens? Here we will have some numbers, like here we will have some numbers. It may be 0 or 1. So we write. So actually here we don't care what are the elements, just we need what. So if we add the elements of first row, what will we get? If we add the first row of this matrix, so we'll get degree of the vertex v1, because first this element will represent the vertex v1 incident with is given how many times. So the number of times vertex v1, is e1 incidence with vertex v1. So second row will be degree of vertex v2 and so on. The last row will be degree of vertex vn. So I'm adding all the elements in a row. So first sum of first row is degree of v1, sum of second row is degree of v2, and sum of n row is degree of vn. What about if we add column wise? So if we add column wise, so we know already that in the property of incidence matrix, the degree of any edge, the entries corresponding to edge e, if you add, you will get only 2. So sum of each, if you add all the elements of a column, so in every column the total sum will be 2 only, because one edge can contribute to only 2 vertices. Okay, so there will be only sum 2. And now we want to add all the entries of the matrix. There are 2 ways. So in one way we added row wise, and now if we add all this, so what is sum of all this? If we add all this, this is summation degree of vi's I from 1 to n. And if we add this, we'll get what? 2, how many times? 2m times. And in both the way, what we are doing, we are just adding all the elements of a matrix, of that matrix. So you add first row wise, and then you add all the elements. So this is the sum of all entries of a matrix. And first you add column wise, then you add them. So it is the 2n. So we added all elements of a matrix in 2 different ways, and both are equal. So since 2m and summation d of vi, okay, so we can write like this, equal, these 2 are equal because both are sum of all entries in a matrix. So So whatever the incidence matrix we have, for any graph you can write the incidence matrix, and in that incidence matrix always you will see, so total sum of elements will be 2n or some degree of px, and that we wanted to prove. So that is the proof. This is a very simple proof. Just we are adding elements of a matrices in two different ways, row wise then column wise. Okay, so let's move to next. So next, the corollary we have corresponding to this result, that so corollary says that number of vertices, so number of vertices of odd degree, number of vertices of odd degree is even. So in any graph, okay, so number of vertices of odd degree is even in any graph. So proof is very simple. Again, this will follow from the last theorem. So what do we know? We know that sum of all degree of vertices I from 1 to n is 2m. So since you can consider 2m is an even number, so you are adding degrees of v1 plus degree of v2 plus degree of v3 and up to degree of vn. So you are adding n numbers, and if in that n numbers you have, suppose let's say you have a 3, 5, 7. Okay, so these three are odd numbers. So if you add them, you get, so you get 3, 5, 7. If you add, so 15. 15 is odd number. So what do you want to say? That this number will be even only if there will be even number of even numbers. So sorry. So what come to the point? That is also correct, but we need what? So if you add odd numbers even number of times, then you get even number. Like 3 plus 3 is 6. Why? We are adding odd number 2 times. 3 plus 3 plus 3. So this is 9. 9 is odd. Why? Because we added 3 times. So if you add an odd number of times, so then we'll get odd number. But what it is saying? Sum of vertices of odd degree is even. So to get the sum even, we must have odd numbers even number of times. Yeah, vertices with odd degree even number of times. So how will we prove? We can go to using contradiction. So let's start using contradiction. So we have to prove number of vertices of odd degree is even. So suppose number of vertices of odd degree, number of vertices of odd degree is not even. So like is odd. Okay, so number of vertices of odd degree is odd. So let me say n. So n we can write in two ways. Let me write it as n1 plus n minus n1. You can write this. So suppose this n1 is odd number. Okay. So the number of vertices of odd degree is odd. Okay. So these n1 number of vertices will have degree odd. So if we add this, then we consider this degree of vi I from 1 to n. So we can break into two parts: degree of vi I from 1 to m, and degree of vi I from m plus 1 to. So next we can go to n. Okay. So this m I have taken as n1, and next is n1 plus 1 to n. n1 plus 1 to n. So since we have considered this n1 is odd number, okay, so we are adding this degree of vi's, and what we have taken, this, suppose the number of vertices of odd degree is odd. So there are if we have odd number of, like if you say, if we break it, so suppose degree of v1 plus degree of v2 and so on, degree of vn1, okay. And actually this sum will be even because we have considered these all vi's where I from n1 plus 1 to n. These are of even degree. So even numbers you add odd number of times or even number of times will always get even. So we have to think about this. So since n1 we have considered odd number, so we are adding, and degree of vertices Okay, degree of vertices with number of vertices with odd degree are odd. We have taken. Okay, so number of vertices like V1, V2, V3, and Vn. These are vertices Vn1 of odd degree. So and n1 is an odd number. So if you add this, what you will get? dV1 is odd number, and degree of V2 is odd number. Degree of V3 and so on. Degree of Vn1 is odd number, and rest is even. So we don't have to care about this is even number. So if you add this odd numbers in odd number of times, okay, like 1 plus 3 plus 5, it may be like that. So odd numbers we are adding 3 times, 5 times, odd number times. So this sum will contribute to odd number, and the rest term will contribute even number. So total you will get odd. But that is contradiction to the fact that this is 2m. So we know from the last theorem that this must be even number. So if we take I, if value 1, 2, 3 up to n1, I've said. So n1 is odd, and the all degrees, degree of v1 plus degree of v2 plus degree of vn without loss of nullity, vn1, these are all odd. So if we add this odd number of vertices have degree odd, then we'll get some odd, and odd plus even is odd. So this is contradiction. So this is contradiction to the fact that summation of degree of bi's I from 1 to n, this is even. So this therefore hence, so our assumption were wrong, so we can correct the assumption. So assumption is, so we can number of vertices of odd degree is even. Number of vertices of odd degree is even. So this cannot be odd. So in any graph, the number of vertices with odd degree must be even. Number of vertices, like for example, let's consider one example. Consider this. So I have taken this graph, so like V1, V2, V3, V4. Now you can rename it. Like V2 you can take here, V3 you can take here. So first, if you add all the degrees, degree of VI's, so just verifying last two results. So degree of V1 is what? 3. Degree of V2 is 3. Degree of V3 is 2. V4 is 2. If you add this, you will get 10. And let's find 2m. 2m means 2 times number of edges. So how many edges it has? 1, 2, 3, 4, 5. 2 times 5, that is 10. So you can simply we verified that degree of vi is I from 1 to here is 4 vertices are there. So this is equal to 2m. And next thing I want to verify. So look, how many vertices are odd degree? So v1 has degree odd and v3 has degree odd. v1 has degree 3, v3 has degree 3. Last we can see V2 and V4. So V2 has degree 2 and V4 has degree 2. So 2 vertices have odd degree. So 2 is even number. So number of vertices of odd degree must be even. You make any graph and you can verify. So next we have complement of a graph. So we'll discuss complement of a graph. Complement of a graph. So if G is a graph, then complement of a graph G is denoted by G bar, okay, and defined by so G be a graph, then complement of graph G is denoted by G bar and defined by, so vertex set in G bar will be same as vertex set of G, and if U will not be adjacent to V in G bar, if U is adjacent to V in G. So since UV are two vertices, so first thing that it has, because the first condition and this is the second condition. If this will not be, UV will not be adjacent in G complement if UV is adjacent in G. So two vertices which are adjacent in G will not be adjacent in G complement, and a vertex set will remain same. So for example, let's consider this one. So V1, V2, V3, V4. We have 4 vertices, and so vertex. This is graph G. I want to draw graph G complement. So in G complement, vertex set will remain same. Just we have to check edge. So edges, like we can see here, V1, V2 are adjacent. So here will not be V1, V2 will not be adjacent. So V1 and V3 will be adjacent. So here V1 and V3 will be adjacent because V1, V3 are non-adjacent in this. And V2, V4 will be adjacent because rest. This is a complement graph. V2, V3 are adjacent in G. So V2, V3 will not be adjacent in G complement. One more graph we can see. This. Suppose this is V1, V2, V3, V4. This is graph G. So what is G complement? So for G complement, so look, V3, V1, V2 and V4. So V1 and V2 adjacent will not be adjacent there. V1, V3 you can join. So you can join V1, V4, V1, V4 and V1, V3 also, because V1 is non-adjacent. So in G, if V1, V3 are non-adjacent, in G complement V1, V3 will be adjacent. Again, V2, V4 are non-adjacent in G, so here will be adjacent. This is graph G complement. So now I will start with. So you can note one thing. If you take again complement of G, you will get G only. Like if you take G complement, you will get G only. This is obvious. Next topic we have degree sequence. So degree sequence of a graph. Degree sequence of a graph. So what is degree sequence? So if graph G has vertices, let's say V1, V2 and up to Vn. Okay, so n number of vertices. V1, V2, Vn. Then, like degree of vertex V1, degree of vertex V2, and so on, degree of vertex Vn. This is called a degree sequence. This is called a degree sequence of graph. So, for example, look this example, this graph. So, like we name it V1, V2, V3, V4. So what is degree sequence? So you can write it anyway. So we are not fixing the order. Just by the labeling I'm writing. So degree of vertex V1, comma degree of vertex V2, comma degree of vertex V3, degree of vertex V4. So if you add it. So what is degree of vertex V1? V1 has degree 3, V2 has degree 2, V3 has degree 3, V4 has degree 2. So this is a degree sequence. And what is degree sequence of this complement? So we have already drawn the complement. That was for this C4. So let me draw the complement. If we take the complement, so V1, V2, V3, V4. So if you take the complement, then you will get what? Only V2 and V4 are non-adjacent in this. Let's have all. Yeah. So what is degree sequence of this graph? So this was for G. I have drawn G complement. So complement, V1 has degree 0 because there is no adjacent edges, or there is no neighborhood of V1. V2 has degree 1, V3 has degree 0, V4 has degree 1. So this is so how can we relate that? If I say you, so if let me write like this: D1, D2, and Dn. this is a degree sequence of graph G, then what is degree sequence of graph G complement? Then question is, what is degree sequence of graph G complement? So what is degree sequence of graph G complement? So what do you think it will be? Okay, so graph has n vertices, okay, like this, n vertices and m number of edges. So how many what will be a degree sequence of the G complement? So if you notice here, it has 4 number of vertices. So 4 minus 3, 1, but it is 0. 4 minus 2, it is 2, but it is 1. 4 minus 3, 1, but it is 0. 4 minus 2 is 2, but it is 1. So what I am doing, I am finding n minus d1, n minus d2, n minus d3, n minus d4, that. But that will not be the case. So here you can note it with like n minus 1 minus d1, n minus 1 minus d2, and so on, n minus 1 minus d3. So this is the degree sequence. So if we know the degree sequence of graph G, we can find the degree sequence of G complement. The remark we have. So degree sequence do not represent the graph uniquely. Two different graphs may have same degree sequence. Two different graphs may have same degree sequence. So two different graphs may have same degree sequence. For example, if you consider a graph with two components, this. So let's say V1, V2, V3, V4, and or anyway, right? V3, V4, V5, V6, V7, V8. So what is degree sequence? So degree sequence will be 2, 2, 2, degree of V1, degree of V2, V3, V4, V5, V6, V7, V8. And we draw this graph. Take this. Okay, V1, V2, V3, V4, V5, V6, V7, V8. So now you see the degree sequence 2, 2, 2, 2, 2. So both have the same degree sequence, but both graphs are different. Okay. So the degree sequence may not represent a unique graph. So next we have a result. So if graph G is connected, like if you have a connected graph, if you take the complement, it must be, So if graph is connected, then its complement may be connected or may be disconnected. So let me give you first, let me give you one example. So we have drawn this graph, this. So this is graph G. If you write the complement, so its complement is this. So what do you notice? Both are connected. So here C is connected and G complement is also connected. So write end. Okay. But what if we write? Okay, we have seen this example also. So if you write the complement, so it is like this. So this is disconnected. If you see, consider it is disconnected. So this is G and this is G complement. And this graph is disconnected because you can write it, you can also draw like this without intersecting edge. So you can see it has two components. This is G complement. So G is connected, but here G is connected, but G complement is not connected. So not connected. So means what? If G is connected, then complement may be connected, may be disconnected. But what about the if you have disconnected graph? So like theorem I wanted to write. If graph G is disconnected or not connected. If graph is disconnected, then the complement must be connected. So if you have a disconnected graph, if you take its complement, it must be connected. So how to prove that? Let's prove that. Okay, if you have a disconnected graph, so I've not taken example of disconnected graph. Okay, so first let's verify. Okay, so let's take one example. We take some not connected graph, or like you can see here also. This one is disconnected, and if you take the complement, you will get this one. So this is connected. What I mean, like see, this is one, this is other. So V1, V2, V3, V4. This graph is disconnected because it has two components. Now, if I take G complement, so V1, V2, V3, V4. So complement means V1 addition to V3, V2 addition to V4, V1 to V4, and V2 to V4. So V1, V2, V3, V4. So V2, V3, V1, V4, V2, V4, V1, V3. Okay. So now you see G complement is connected. So if G is disconnected, its complement must be connected. So I will write the proof. So let me write the proof, general proof of this theorem. So what we have given? We have given a connected graph. We have given a disconnected graph, and I wanted to prove that its complement is connected. So we have given graph G is disconnected. So question is, what is definition of this disconnected graph? So the definition of disconnected graph is there exists a partition X and Y. So there is a partition, there exists a partition X and Y such that there is no edge from a vertex from X to a vertex from Y. So like we graph it disconnect because you can partition the vertex set, like vertex set of G can be partitioned into set X and Y, where X and Y are empty, I mean disjoint, and union is this, but there will not be any edge from this to this. Okay, so means disconnected. There exists such. Okay, what we have to prove? So we have given this G is disconnected, so we'll get one partition X and Y such that there is no edge from vertex of X to vertex of Y. There is no edge. What we have to prove? So we have to prove G complement is connected. We have to prove G complement is connected. So what is the meaning of definition? That is what we want to prove. So G complement is connected means for every partition of vertex set of graph G. So every partition like x1, x2. Okay. So let me in general name it x1, x2. For every partition x1 and x2, x1 and y1. So whatever you take, for every partition x1, y1 of vertex set of G complement, there is an edge from a vertex of x1 to a vertex of y1. So since G is connected, you take whatever partition you want to take, x1, y1, there must be one edge from this. Okay, and there is one partition. In case of G, there is one partition. Okay, and here is for every partition you will have this, because G bar is connected. We have to prove this claim. Okay, this claim we have to prove this. And again here also x1 union y1, if you take, So this is vertex set of G complement. Okay, and x1 intersection y1 is going to be 5. x1 intersection y1 is 5. And what we know we know the definition of complement. Okay, if UV are adjacent in G, then UV will not be adjacent in G complement. UV are vertices. One more thing. Since we know that in case of complement, vertex set are same, right? Whatever we know, vertex set of G is same as vertex set of G complement. And this claim also says that x1 union y1 is same as x union y, because x1 union y1 will give you the vertex set of G complement. Okay, so you can write complement and x union y. So x1 union y1 will be kept same as x union y. Vertices are same, just it is different. So how to prove the claim? So what we can think that we'll prove this in cases. Okay, so if this x1 and x, so first case I can take if we have x1 intersection x, this is non-empty, and y1 intersection y, this is non-empty. Both are non-empty. So x1 and x has some common element, and y1 and y has some common element. This we assume, okay, in this case. So like suppose x is an element x1 intersection x, and suppose y is element y1 intersection y. So x belongs to here x1 and y belongs to y1, right? Now here you can also say x belongs to x1, since it is an intersection, so x belongs to x also and y belongs to y also. So what do you see? Since x and y are is in G, then what is the definition of G bar? So that x and y will not be is in G complement. That will not be, I mean x and y will not be adjacent in case of G complement. So same x and y we are taking. Okay, so what we proved? Okay, so but we wanted to prove the opposite. So x, y are not adjacent in G. Okay, then x, y will be adjacent in G complement. So since what we have taken, see here we have taken a partition x and y. Okay, so small x is one element here and y is this. So we know that x and y will not be adjacent to each other. There will not be any edge from x to y. But the same x we are taking here in case of this, in this particular case, okay, not in general. So since we are taking x in the common, okay, y in the common, so x, y are not adjacent since graph G is disconnected. But x, y will be adjacent in G complement. X, y are not adjacent in G, but x, y are adjacent in G complement. How it follows? From the definition of complement. From definition of complement. Okay. This is part 1. So we proved that x and y are not. What we proved here? G is disconnected. Then this, because x, y are arbitrary. So second case we have like suppose this is x1 intersection x is empty, or this. So we can, they are equivalent cases. Okay, so if you take, so without loss of generality we can consider one of these two things. Like if you take one case, x1 intersection x is non-empty and the other is empty. So case 2 I am talking. So in case 2 actually what I am considering. So without loss of generality, like we can consider this, start with this or this, anyone, and both will give you a similar proof. So I'm starting with this one, okay, and without loss of generality we can write this for this too. So let intersection x, this is non-empty only, others may be empty or this. So, and okay, consider the case, and y1 intersection y, this is empty. Okay, so we have taken one case, x1 intersection x non-empty, both are non-empty. Now one is non-empty, other one is empty, and same two will follow like this. If you take this non-empty and this empty, because without plus unity, both will follow. So I'm doing for one case. So the second case will be similar. Third case will be similar to second case. Okay, so what I'm taking, this is empty. Y1 intersection y is empty. So this is non-empty. So let's take one element in x1 intersection x. Okay, and since y1 intersection y is non-empty. Okay, but you remember this, x1 union y1 was equal to x union y. Okay, so we have taken x, small x as in, since it is non-empty, so there must be one element, so we have taken small x as x1 intersection x belongs to this. And now, so this has some common element, but these two do not have common elements. Means what? So all the elements of y will be in x1 and all the elements of y1 will be in x. So from here, what follows, that since x1 and x has some common element, but y1 and y do not have any common element, but union are same. So y1 will be subset of x and y will be subset of x1. Yes. But what we need to prove? We have given graph G is connected and G bar is not connected. We have to prove that. So x we have. I want to find one more element. So here small x is in x1 and small x is in x. Okay. So see, since y set cannot be empty because in partitions we consider both set are non-empty. So since y is non-empty, so there must exist one element in y. Okay. So, or you can say there exists some element, let me call it z, in x1, or we can take in x. Okay, there must element z in x, such that so we must, since y is not okay, I'm consider y. So y subset of x1. So every element of y is in x1. Okay, so there exists one element in x1. That will be such that since all elements of y are in x1, so there must exist one. You will find one element in x1, that's z. That z in y. Okay, so that z belongs to y. And now z belongs to y and x belongs to z. So what can you say about xz? So we have taken xy, we have taken xy as partition of G such that x is not adjacent to z. So x is not adjacent to z because xy are partition of this. One such partition we have considered in G. So what will it imply? By definition of complement, x and z will be adjacent in G complement, and that's what we wanted to prove. So we have taken one element in x, okay, and other in y, so that are not adjacent, but we get that in G complement. And the third case is exactly similar to this. So case 3, if you take like x1 intersection x is empty and y1 intersection y is not empty. So same case will follow, like similarly will follow. You take y belongs to this, y1 intersection y, okay, and since you see here that x1 intersection x is empty, so in a similar manner x1 union y1, we know that x union y. So that's why what will happen. So since y1 and y has nothing common, okay, sorry, y1 and y has something common because it is non-empty, and x1 is x1 and x has nothing common. So all the elements of x1 will be in y and all the elements of x will be in y1. So it's a set theory, okay? Two sets has same union. So if y1 and y has x1 and x has nothing common, so all the elements of x1 will be in y1, and since x1 and x has nothing common, so all the elements of x will be in y1, and the same it will follow. Okay, there is just so here we get y belongs to capital Y and y belongs to y1. So y we have, and since x is non-empty, so you can write since x is non-empty, so there exists some z in y1 such that z belongs to x. Now you see z belongs to x and y belongs to y, so yz will not be adjacent in G, and this will imply yz will be adjacent in G complement, and y is in y1 and z is in zy. Okay, 1 minute. So I have to take here y. Yeah, that's fine. That's fine. The same both cases. Yeah. So yz not in the same G, but the same yz are adjacent in G complement. So just we are proving that the part where it is connected, so that will be connected in the complement. And the fourth, the case is both are empty. Both intersections are empty. Right? First we have taken both non-empty. Second one empty, non-empty, empty, non-empty. Both are empty. So x1 intersection x is empty, and y1 intersection y is empty. And what we know already? We already know x1 union y1 is equal to x union y. So what can you conclude from here? x1 and x has nothing common. So all the elements of y1 is in y. Okay, and all the elements of, okay, you consider both at a time. So say x1 and x has nothing common and y1 and y has nothing common. x1 and x has nothing common, y1 and y has nothing common. So means all the elements of x1 will be in y and all the elements of y will be in x. All the elements of y1 will be in x and x will be in y1. So like x1 is y and y1 is x. So both, now you simply see that like x belongs to x, y belongs to y, and x, y will not be adjacent in G, and that will imply what? So that x is in y1 and that y is in x1. So that xy in G complement will be adjacent. So means we get an A's from x1 to y1. Yeah, so we have already proved what we have seen, that if graph is disconnected, then complement will be connected. If it is connected graph, then complement may be connected, may not be connected. So today I will stop only here. In the next class, I will discuss this very important theorem, Havel-Hakimi theorem. Havel-Hakimi theorem. This is very important theorem, and this discuss about the graphics. Okay, degree sequences graphics or not. So I will discuss this in next class. Thank you.